All right, so we're going to review different ways that we can view sequences, the different ways that we can write the formulas. So what I would recommend is after I do the first example all the way through, you pause it between each example. So I could be given a list of terms. Remember, a sequence is just a pattern in which the next term is predictable. So I could predict that the next number is 17. How did I know that? The verbal description tells the person where to start and what the pattern is. So start at 7 and add 2 to the previous term. So if I keep adding 2, adding 2, adding 2, I know that this is an arithmetic sequence. It could be arithmetic, geometric, or neither. So adding is arithmetic. So I'm going to say what type of sequence I have. And then I'm going to write the closed formula and the recursive formula. So the recursive is the one that we learned how to do first. To do the recursive, we first tell the person where to start. My starting term, term 1, is the number 7. Then we have to write it as a sub n. So to get the term I'm looking for, go to the previous term, which would be term n minus 1, and we want to add 2. So the rule kind of goes here at the end. So you tell the person where you're starting and how much to add each time. The closed form allows us to find any term that we want simply by plugging in the number. And it's written a little bit differently. A of n, we write down where we start. So we always put where we start. And then we write down what to do. I need to add 2 n minus 1 times. The reason it's n minus 1 is because I don't want to start adding 2 until I get past the number 7. So I assume that this is term 1, 2, 3, 4, 5. So to find term 2, do you see how when you plug in the number 2 here, I'm on 2 minus 1 is 1, 1 times 2. I'm only adding 2 one time. So 7 plus 2 is 9. When I get to the third term, 3 minus 1 is 2. 2 times 2 is 4 plus 7 is 11. So this allows us to add 2 n minus 1 times. Over here in this n minus 1, the a in front of it tells us that we're not plugging anything in here, we're just referring to the previous term. So when n is used without the a in front of it, you're actually plugging a number in for that n. So I would recommend pausing the video and trying example 2, and then I will put the answer up. Okay, so this says the first term of the sequence is 10, and each term is 4 less than the previous term. So 10, and I'm going to subtract 4, so I'd be at 6, and then 2, and then negative 2, and then I could keep going. So how could I decide if that's arithmetic or geometric? Subtracting is like adding a negative 4. So this is also arithmetic. And how could I write it in closed form? Well, I'm going to do recursive first. In recursive form, first you say what you're starting with. So my starting term is 10, and a of n equals a of n minus 1. What am I doing? I'm subtracting 4 each time. So this is recursive. Now I'm going to write it in the format of closed form. So a of n equals what I'm starting at. I'm starting at the number 10, and I'm subtracting 4 n minus 1 times. The one thing that I haven't written so far is that inequality to tell you what n could be. So in each of these cases, I'm using n1 as my starting term. So the rule is good for n being 2 or greater. So if you want to write the inequality to show the person what n could be, you could write n is greater than or equal to 2. If this part confuses you, I would just leave it off. I would just write this part of the formula and you're going to be correct. Okay, so let's see. On this example 3, you're going to pause it and try it first. Okay, so here's my closed formula. So a closed formula always tells you where to start and what to do. I'm going to multiply by 2 each time. So let's write our sequence first. Start at 6, multiply by 2, that would be 12. Multiply by 2, that would be 24, and then 48. I could write dot, dot, dot. Multiplying is a geometric sequence. And what am I doing verbally? So start at 6 and multiply by 2. One other question I could have asked on here is growth factor versus rate of change. So arithmetic always has rate of change. This would have a rate of change of -4, whereas this one has something called a growth rate of 2. So if it's geometric, we call it the growth rate, what you're multiplying by. And if it's arithmetic, we call it a rate of change, and it's what you're adding each time. So I'm adding -4 each time. So our last piece is the recursive formula. So I tell the person where to start. So A of 1 or F of 1, whatever you're going to name your sequence. A of n equals A of n minus 1, and I'm multiplying by 2 each time. And then if I wanted to say n is greater than or equal to 2, I could also add the inequality. Okay, so pause and try the fourth example now. So I've given you this recursive formula. So we need to generate the sequence, and it tells me my first term is 10, and to find the term I want, I'm going to the previous term. Recursive means go to the previous term, and I'm going to add 3 each time. So I would be at 10, adding 3 is 13, adding 3, and adding 3. So I just said adding, so that means that this is an arithmetic sequence because I added 3. And I'm gonna start at 10 and add 3 each time. All right, so how do I write that in closed form? This was called F. I'm just gonna call it F over here. F of n equals 10, and I'm subtracting 3 n minus 1 times for n is greater than or equal to the second term. All right, so there are 4 more examples on the back. So what I would do is pause the video, and I am going to come back and show you the answers kind of all at once. I actually can't pause. I can only stop. So I'm going to kind of quickly go through these. 100 and then 50 and then 25 looks like I'm multiplying by 1/2 each time. So that tells me that this is a geometric sequence, and I'm starting at 100 and multiply by 1/2. Closed formula. Make sure that when you write the closed formula, you remember that this is an exponential function. So the n minus 1 goes up in the exponent, so I can do 100 times 1/2 times 1/2 times 1/2. And then the recursive formula, you say where you start. So my first term is 100, and A of n equals A of n minus 1 times 1/2. I don't need an exponent here because I'm just multiplying by 1/2 each time. Here, multiplying by 1/2 more than once, I need the exponent to show it's times 1/2 times 1/2 times 1/2. The first term of the sequence is 5, and it has a growth factor telling me that I'm multiplying of the sequence is 3. So times 3 and times 3 and times 3. So it's geometric if it's times 3. And my closed formula, A of n equals 5 times 3 to the n minus 1 power for n is 2 or greater, because I'm starting at term 1, and then so term 2 gets plugged in here. And A of 1 equals 5, A of n equals A of n minus 1, and I'm timesing it by 3 each time. All right, the next example, I have the recursive formula. So this is a little bit of a different one. I'm starting and giving you term 1 and term 2. So I know that this sequence goes 2 and then 8. This formula is the Fibonacci relationship where you're adding the two previous terms together. So the previous term and then two terms before it. So I'm going to add 2 plus 8 to get 10, and then 10 plus 8 to get 18. This is not arithmetic or geometric. If you knew, it's kind of the Fibonacci pattern, but you don't have to know that. But adding the two previous terms, Fibonacci starts at 1, 1, but this started at 2, 8. So the first term is 2, and the second term is 8. Add the two previous terms. And there's no closed formula. It can only be represented recursively for Fibonacci. Okay, the last one, how do I go from 4 to -4, 4 to -4? I'm actually multiplying by -1 each time. So start at 4 and multiply by -1. So that makes it geometric if I have a growth factor. And it would be a of n equals 4 times the number -1, and you want to put the -1 in parentheses, so the -1 gets squared and cubed, and that's what's making it change from positive to negative. And we're going to say a of 1 is 4, a of n equals a of n minus 1, and we're multiplying by -1 each time. And if we want to say for the second term onward, we could do that.